Okay, so I am the only thing standing between you and dinner. So I will be brief, maybe 2-3 hours tops. So if you're of a certain age, that is my age, you were experienced primary school reading 2 or 3 of the same poets every year for about 8 years. And one of them was Robert Frost, and he wrote this very prescient poem, maybe his most famous poem, which goes, "Some say the world will end in fire, and some say in ice." And so I'm here to tell you which is the more likely fate of the universe, and we'll come to an answer today. Now, I want to add a caveat, and the caveat is very well-known saying by a couple of philosophers. The fellow at the top is Yogi Berra, who was a catcher for the New York Yankees, and at the bottom is Niels Bohr, and I have to put them both up because the quote is attributed to both of them. And the quote, of course, is, "Prediction is hard, especially about the future." Now, they never worked together as far as I know. And in fact, it's likely that this is the first PowerPoint slide they've ever shared. But Berra was a lifelong faithful Catholic, as well as being from my hometown of St. Louis, and so I will rely on him as the main philosopher for the rest of the talk. We'll see what he has to say in a bit. Okay. So the Big Bang Theory had a number of fathers, but only one real father, and that was Father Georges Lemaitre, who developed it in several papers between 1927 and 1931. Now, there were, of course, precursors. At the time, Hubble had discovered not only that galaxies were all moving away from us, that the universe, but that the speed of precession was, or the speed of recession was proportional to their distance. And that turns out to be a unique feature of an expanding universe that lacks a center of expansion. And so this was known in the late 1920s, and simultaneously, Friedman, working with Einstein's equations, showed that they could give you a metric in which the ruler of your metric was expanding with time. And these two didn't really put these things together. Now remember, this was the pre-internet age when information traveled slowly, and it was really Lemaitre who had a foot in both camps. He was talking, he had gotten his Ph.D. in relativity, and he studied under Arthur Eddington, who was a very famous relativist at the time. But he also was in contact with the people doing the observations. And so he was uniquely placed to pull together the theory and the observation and to give us the modern theory of the Big Bang. And this theory was something of a backwater for maybe 30 or 40 years after he produced it. And in that time, there was one key question which cosmologists were trying to address. And I'm going to illustrate it first with a prop here and then with a little motion thing. So here's I just happened to find these under here, and I'm going to now toss them into the air and catch them. And you see that the faster I toss them, the higher they go. And so you can imagine that eventually I would give them enough velocity that they would escape the Earth's gravitational field entirely and go out into space. And that's completely, it's like 5 miles a second, but it's completely within your imagination. And the universe as a whole has a similar behavior. So let me show you one of my few animations. The universe can expand forever, escaping its own gravitational field. And here's an example. Here's the apple going up into space and into orbit. Not into orbit, into, leaving the Earth's gravitational field. Or the universe could expand for a while and then recollapse under its own gravitational field. And this is actually parallel to the problem of throwing something in the air and figuring out how fast it has to go to escape the Earth's gravity. And it's a standard sort of first-year physics problem we give students. Essentially, you figure out what the kinetic energy is of the object, and you figure out what its potential energy is due to the Earth's gravitational field. If the kinetic energy is greater than the negative of the potential energy, the kinetic energy wins and it flies away out of the Earth's gravitational field. If the kinetic energy is less, then it falls back to Earth. Now, the interesting thing is that it's the question of whether the universe will expand forever or recollapse is sort of the inverse of this problem, in the sense that With the Earth, we know the mass of the Earth, so we know the potential energy. And what we can vary is the kinetic energy. With the universe, we know the kinetic energy of distant galaxies because we measure their recession velocities very precisely, but we don't know, or until recently, we didn't know the potential energy of the universe. That is dependent on the total mass of everything in the universe. Now, we've got a much better answer to that question now, and I'll show you that in a minute. But essentially, from about 1930 to, say, 1998, these were the fates of the universe people were interested in. That is, you could have the closed universe is a high-density universe. It expands and then recollapses. Let me see if I can master it. Here it is. So it expands and it recollapses. An open universe expands forever, and a flat universe is exactly balanced between the two. That's where the kinetic and potential energies are exactly equal, and it expands forever, but is continually slowing down. However, as is often the case, the universe threw a curveball at us, to continue the baseball analogy. And the reason is that in the late 1990s, several groups were trying to determine which of those curves we live on. And you can't actually look into the future, obviously, but what you can do is look into the past and measure how the expansion looked billions of years ago. So, does anybody remember this? Anyone over the age of... You do? Good. My mother thought this was an educational show because it was the only science fiction show she let us watch because it was all about history. So if you look at a galaxy that's 10 billion light years away or 5 billion light years away, that's a measure of what the universe was like 5 billion years ago. And the universe is only 14 billion years old. So what two groups were doing in the 1990s, in the late 1990s, was to measure the expansion rate of the universe at early times and then extrapolating to figure out which curve we were on. And it turned out that all of the answers were wrong. It was none of the above. And here's a picture of what is actually going on. So this is our classical universe that expands and recollapses. The blue and the red curves are universes which expand forever. And the universe that we actually see is on none of these three curves. And nobody expected that. That was a case of, who ordered this sort of physics. What we actually ended up with is living on this red curve in which the universe has been expanding, slowing down, and then recently, right here, it's been speeding up again. So this is rather remarkable. It's as though I took an apple and I threw it into the air. See if I can get it to go. Yes. And it initially slowed down, and then when it got a few feet into the air, it accelerated away from the Earth. So this was the discovery of what has been called dark energy, and it's been one of the main puzzles in cosmology. Again, it was discovered in 1998, and people have been puzzling over it then for almost 30 years now, trying to figure out what the correct model is. So we need dark energy, and dark energy has some very weird properties. So it produces repulsive gravity. In order to have something accelerate, you actually have to have repulsion. Now, we learn in grade school Newtonian gravity. Newtonian gravity is always attractive. But it turns out that in the theory of relativity, you could have circumstances in which gravity becomes repulsive, and we think that's what's going on here. So this dark energy produces repulsive gravity as opposed to attractive gravity. We think that it doesn't cluster, that it's smoothly distributed throughout the universe. We think that it probably only feels gravity. It probably doesn't couple to any other fields in the universe. And the most likely explanation is that it's what's called a cosmological constant. That's a special form of dark energy. It's the energy of the vacuum. A cosmological constant has the property that its density stays constant as the universe expands. And that should bother you, that idea. Because if I have a box full of matter and I let the box expand, the density goes down as the volume of the box. The amount of matter in the box is fixed and the volume goes up, so the density goes like 1 over the volume. And the same thing happens in the universe as a whole. The density of ordinary matter averaged over the whole universe goes down as the universe expands. But this cosmological constant has the unique property that as the universe expands, the density just stays the same. So that's weird. It should bother you. Okay. And both Einstein and Lemaitre had an interesting relation to the cosmological constant. Einstein was the one who postulated it first, but for a completely different reason. He realized that his equations predicted a universe that should be constantly expanding or contracting, and so he introduced this to make a static universe because that's what people believed at the time. The universe was just fixed. It was static. Later, when it was discovered that the universe was expanding, he took the cosmological constant out, and he said it was the greatest blunder of his career because if he had not put it in to begin with, he could have predicted the expanding universe. He could have been even more insanely famous than he already was. We now know that taking the cosmological constant out was the greatest blunder. He should have left it in because 90 years later they would have confirmed it. And Lemaitre, on the other hand, believed that there had to be a cosmological constant. He actually put it into his equations basically on philosophical grounds. He said there has to be some kind of energy of the vacuum, and so there ought to be a cosmological constant there. So he actually, in some sense, was the first to predict that there ought to be a cosmological constant. Now, this has profound implications on the future evolution of the universe. If you remember that picture, the universe is actually accelerating as it expands, and so that drives the expansion faster than it would if it was one of those other curves I showed you. So, for example, there's something called a cosmological horizon. So at any given time, you can only see a finite distance in the universe. The universe is about 14 billion years old. If you multiply that by the speed of light, that's the most distant information or light that can reach you since the Big Bang. So when people say, is the universe finite or infinite, I say, I don't know and it doesn't matter because you can only see a finite part of it, even if it is infinite. But what happens is, as the universe expands, the horizon goes up because time is going up. But in these models with a cosmological constant, the galaxies expand even faster than the horizon does. So here's my pathetic animation I put together last week. So you see that as time goes on, objects get driven outside of the horizon and disappear from our view. So what does that mean for the expansion of the universe? Well, here's a Scientific American article I wrote a few years ago. On the left-hand side, we see the sky now from a dark location, not here, but someplace where there's not a lot of light. And then in about 5 billion years, which is not that long in cosmological times, I mean, the age of the universe is 14 billion, the Andromeda galaxy is moving toward us and will actually merge with us. And we'll actually just be in the middle of one kind of super galaxy, the Milky Way Andromeda galaxy, plus a few other galaxies gravitationally bound. And that's not a catastrophic event. People think, oh, that means stars will collide. And the stars in a galaxy are pretty far apart. And so even when they collide, the chance of two of the stars colliding is pretty remote. But we'll be in the middle of a super galaxy. And that sun is getting awfully big there. We'll talk about that in a minute. What happens in about 100 billion years, and this is work I did with Lawrence Krauss, we pointed out that in 100 billion years, you won't be able to see other galaxies. We'll just be in the middle of an island of stars, and in fact, the universe kind of wipes out all evidence of cosmology. So in 100 billion years from now, people won't actually be able to see an expanding universe. They'll think we live in a classical 19th century island universe with nothing, no expansion. So that's unfortunate. After 100 billion years, we won't be able to do cosmology, but that's not a problem because in only 5 billion years, the Earth will be incinerated as the sun expands and we find ourselves inside the surface of the sun. Now, this actually has been called into question. There's a paper by Adams and Laughlin where they argue that enough material will be expelled from the sun as it enters this phase for the Earth to be pushed into a higher orbit, so that we'll actually be orbiting outside the radius of the sun. And so that's another possibility. It doesn't mean things will be hunky-dory because, we're kind of well adapted to our current orbit and our current sun, but probably not too good. And then in about 100 trillion years, a blink of an eye, practically, compared to some of the numbers I'm going to show you soon. In 100 trillion years, the last stars will burn out. The dwarf stars are the longest-lived stars, but even they eventually give up and use up all their fuel and burn out, and then the universe will go dark, and that will be the end of it all. And so the universe will end in ice. But, as a famous philosopher once said, it ain't over till it's over. So people have speculated about what can happen after this, and some of the people I talked about, I'll give you some references at the end, but Laughlin and Adams wrote a book and an article about the future evolution of the universe after this point, and one possibility is proton decay. Now, the proton appears to be stable, and some people think it's absolutely stable, but a lot of particle theories predict that it ought to decay. And there was a big effort in the early period of my career to measure proton decay because it was a prediction of all these grand unified theories. And they never saw it. So what we've done is put lower limits on the age of the proton. But Laughlin and Adams pointed out that if the proton was unstable, basically all bound objects would eventually decay into a sea of elementary particles. What if that's not the case? What if matter is absolutely stable? Well, then there's an even more bizarre possibility, which was first discussed by Freeman Dyson back in the late 1970s, and it's based on quantum tunneling. So in classical mechanics, you can't move past an object if you don't have enough energy to do it. But in quantum mechanics, there's a small probability that you can actually go through a potential barrier and emerge on the other side. And this is observed. I mean, this is not just science fiction. We know that this happens. So, for example, if I walk into that wall, there's a small chance that I will, in fact, tunnel through the wall and emerge on the other side. So let's try it. So that was a failure, but that's just one experiment. So maybe I could happen the next time. Well, no, it's very, 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 very unlikely. But if you have an infinite amount of time, things that are very unlikely become certainties. So what Dyson pointed out is that you could actually have a star, a dead star, maybe a remnant of a white dwarf or a red dwarf, could actually tunnel through its Schwarzschild radius and turn into a black hole. Now that sounds insane, and it's only insane in terms of how long it would take. He calculated that it would take 10 to the 10 to the 26th or 10 to the 10 to the 76 years. So that's a number that is so large. I hate to say astronomically large because it's more than that. It's cosmologically large. That's a number so large you can't even write it down. That's a 1 followed by 10 to the 26 zeros. And in fact, as somebody pointed out, it doesn't even matter what units you use. It could be years, it could be seconds, it could be, ages of the universe. They're all pretty much the same when you get to those kind of numbers. And so the idea is that everything would collapse into black holes, and then Dyson predicted it would all decay into Hawking radiation. And so once again, the universe turns into a sea of elementary particles. And so it's over. Even though it ain't over till it's over, it's actually, in this picture, it is over. So this suggests that the world will end in ice, one way or the other. I mean, some of these are more speculative ideas than others, but this is kind of our standard picture. If the universe is dominated by a cosmological constant, then there will inevitably be an era when everything is driven outside the horizon. There will inevitably be an era where stars will burn out, and the only thing that's going to happen after that is some more esoteric processes. And of course, there may be things we don't know about that would change those predictions, but the first part of it is almost certainly true. On the other hand, the cosmological constant is not the only game in town. It is the most likely game, but it's not the only one. And if you've followed the science news, there was a recent publication about a year ago by the DESI collaboration, which argued that maybe the evidence is that we don't live in a cosmological constant universe. Maybe we have dark energy whose density is going up or going down. I was delighted by this because this is what I've been working on for a while. And it's not clear that that's really the case. I mean, people are still arguing. And if you took a straw poll of cosmologists, I'm sure 3/4 of them would say Yeah, it's a cosmological constant. But there is a chance that it could be something else. And the weirdest possibility among those is called phantom dark energy, which was first proposed by Rob Caldwell back in the around the turn of the millennium. And it's even weirder than a cosmological constant, because in this type of dark energy, the density goes up as the universe expands. Now, you can imagine a kind of dark energy where the density would go down as the universe expands, and that's also a possibility and is much more likely. This is even more weird, and it violates some of the reasonableness conditions of relativity. There are things called the energy conditions, the strong energy condition, the weak energy condition. They're more axioms than things that are predicted by relativity, and this violates some of them. And so it does produce a lot of theoretical problems. And so most people would bet their money against this. On the other hand, it's actually consistent with the observations. If you actually say, what is the dark energy doing? A dark energy with this kind of behavior is, in fact, perfectly consistent with what we observe. So let's explore what happens in this case. Well, in this case, instead of having a universe which gradually expands and then accelerates exponentially, what happens is this is cosmological constant here. It basically goes to an exponential curve. If we have phantom dark energy, the expansion of the universe asymptotically goes to a vertical asymptote. That is, the scale factor, this factor measuring the separation of objects, and the density of the dark energy both go to infinity at a finite time. And this has been dubbed the Big Rip. Because what happens is all bound structures at that point get torn apart by the force of the expanding universe. So it starts at the edges. The most weakly bound objects are clusters of galaxies. They would dissociate. Then the galaxies themselves would dissociate into stars. These planetary systems would be torn apart. And then as the density gets higher and higher and higher, even atoms would be ripped to shreds. And there would be a future singularity, which would be kind of incomprehensible. We don't really have the physics to describe exactly what would happen, but it would be bad. So should you be afraid? That's a good question. Well, generally not. Because first of all, it's an outlier theory, so it's kind of, it's fringe. I've written papers on it, but it's fringe. It's a fringe theory. We agree to this. But in most scenarios, a big rip cannot occur in less than about the current age of the universe. In other words, the kind of gentle big rip requires about, of order the current age of the universe. So it couldn't happen in less than 14 billion years or so. And so we don't have to worry about it, probably. But there are also, and I blame myself for this because it was my idea, there are even more exotic scenarios in which a big rip could occur sooner, for example, before I finish the talk. And that would, I think we can all agree that would be a tragedy. So why is that? Well, imagine that all of our ideas about what the current density of this dark energy is are based on cosmological observations. And I told you that cosmology relies on distant galaxies, and so we're really measuring what the expansion of the universe looked like 1 billion years ago. We're not measuring the expansion of the universe right now at this very instant. That's impossible. And so it is, in theory, possible for this phantom dark energy to suddenly start driving the expansion of the universe, and we wouldn't even know about it because the information from these distant galaxies wouldn't reach us in less than a few billion years. And so we dubbed this imminent dark energy, and I sat down with my student to figure out what kind of constraints you could put on it, because come on, we know that I'm going to finish this talk, and we're going to finish dinner too. So we thought, what kind of constraints could you actually put on this stuff to put a lower bound on how soon the universe could be ripped apart? And it turns out that there are much less stringent constraints that arise from the orbits in the solar system. So those of you who are old enough remember the Apollo moon landings. My students don't remember them and don't actually know that we went to the moon, but I remember watching them on TV. And one of the details was they left a laser reflector on the surface of the moon. And so people who complain that there wasn't a lot of science in the space program are wrong, because that laser reflector allows us to measure the orbit of the moon with incredible precision. And that allows us to measure any variation, for example, in the gravitational constant with enormous precision. And so there's been a series of measurements, both the orbit of the moon and the orbit of Mars and then planetary orbits, with increasing precision, and they tell you that basically, no, there is no extra force on these planets that's driving them apart. And it's not a very stringent constraint because, well, the force could be increasing with time, and we don't know. But we were able to actually put a limit and say that there's not going to be a big rip in less than 30 years. So that's the best you can do with the solar system. Now I'm willing to concede somebody else out there could do a better job. So our paper's out on the archive. You can figure out what we did wrong. I mean, the argument is correct. I mean, there will not be a big rip in less than 30 years, but you might be able to put a limit of 1,000. We were disappointed that the limit was this poor. It's kind of sad, really. So to rephrase Robert Frost, the world will probably end in ice, but that conclusion is still subject to change. So that's why cosmologists don't write poetry. But this is in fact the best we can do. That is, a cosmological constant is probably the most likely scenario, and a universe which becomes cold and dark is the most likely outcome. But there still are other interesting possibilities that people have talked about. Now, there are other theories out there that are sort of again not mainstream in the sense that most people aren't working on them, but they're not crazy either. So Paul Steinhardt at Princeton and his collaborators have worked on a theory called the ekperiodic universe, in which the universe actually undergoes periods of expansion and contraction, and expansion and contraction, and he's basically trying to resurrect the idea of an eternal universe. Because in the old days, people looked at the collapsing universe and said, well, maybe it could just bounce. It'll expand and collapse and expand and collapse, and so it'll be eternal. That turns out not to work because entropy goes up with each bounce, and so you don't really get the same result. You don't get a universe that looks the same with every bounce. In his theory, in the ekperiodic universe, the universe does look the same every time it bounces. And that allows you to have a universe that's sort of eternal. But it's a controversial theory. The main people working on it are he and his collaborators, but it's an interesting alternative. If you're interested in reading more about this, Freeman Dyson was really the first one to discuss what has become known as cosmic eschatology, the end of the universe. And he wrote a really interesting paper in 1979 that kind of set this field in motion. He was actually interested in whether life could survive forever. So all his calculations of collapsing matter, collapsing into black holes, and the black holes dissolving, these were all secondary to his main goal, which was to argue that life could exist forever in the universe if we simply went into hibernation every so often and slowed down our metabolism and that sort of thing. I don't think that's the main interest in his paper. The main interest is, in fact, these speculations on decaying black holes and neutron stars. Adams and Laughlin, I mentioned that. Oh, what happened? What a mess. There we are. How do I get out of the... Oh, it doesn't matter. Adams and Laughlin wrote a paper kind of exploring these ideas in more detail. The timing was very bad because it came out right before the discovery of the cosmological constant, so it wasn't incorporated into their discussion. But they also wrote a popular book called The 5 Ages of the Universe, which you can get if you're interested in the topic. Caldwell, Kamiankowski, and Weinberg were the ones who came up with the idea of the Big Rip, and then I had done some stuff on the end of cosmology, and then this recent paper with my student, which indicated that the Big Rip would not occur before I retire, which, of course, is the key milestone here. Okay, so I'm going to stop there and take questions now.